All right, we are ready for our next fireside discussion. And for this talk, I want to bring on Juan Benet, founder of Protocol Labs. We're going to talk about InterPlanetary Consensus, IPC. So please join me in welcoming Juan on stage.
Thanks for having me.
So there's a lot of interesting things happening here at the Protocol Labs universe. So let's start with, what is IPC? I feel like you would have called it work done when the interplanetary file system existed, but we got to get to the consensus level. What's going on?
Yeah. So as we were building things like IPFS and Lip2P and Filecoin, we got a very good sense of all of the scalability problems that this kind of tech has, and we've run into a very clear, like an obvious present problem with the entire industry, which is there's no single strong consumer app that in the Web3 space, right? Like today, when you use your normal phones or computers for doing your daily tasks, almost nothing, none of the applications that you use on a day-to-day basis actually use Web3 and the crypto space. And that's fundamentally because the scalability of the tech is not there yet. Meaning you cannot actually build good social networks. You cannot actually build good productivity software. You cannot build any of the normal types of applications that normal humans use with current Web3 tech. There's a huge gap in the scalability of these technologies to actually be able to give the right tools to developers to build those kinds of things. So IPC is a technology that we're building to solve that problem specifically. We think the current generation of, like the current next generation of crypto networks are improving the scalability story significantly, but they're very, very far away from actually reaching the full traditional Web 2 level of scalability. Meaning we need to be hitting trillions or quadrillions of objects tracked and transactions, not, kind of like the current like 10,000 TPS or like 100,000 TPS. We need to be hitting billions of transactions per second. Like that's what it means to be at true large scale. And so in order to get there, blockchains are going to have to change a lot in terms of their structure. And we found like a good straightforward path to go from where we are today to that kind of future with much higher scalability. And that's what we're kind of building through IPC. It's called IPC, Interplanetary Consensus, because it builds on the same principle that IPFS builds, which is the interplanetary principle. If you design a system, a distributed system, to work across planets, and you force yourself to make it have like good real-time guarantees in that setting, like really imagine the thing that you're building working on Earth and working on Mars and working across the two planets.
And just to make it clear that this is specifically the variable being just a time delay for the information syncing.
Yeah, exactly. So between Earth and Mars, there's a huge time delay because it takes a long time for signals to pass through space. It's like an 8-minute delay between Earth and Mars. If you have that in a normal HTTP request, imagine that you try to load a web page and you have to wait 8 minutes for the server to come back. Like that's obviously doesn't work, right? That's kind of the fundamental same principle that I used to build IPFS. Similar with blockchains, if you think about a system that has to work at that range of scalability, you end up with a very different architecture. And kind of the reason why this principle is helpful is that the kind of like intuition that you have about a latency of like 8 minutes is the same kind of intuition that you should be using for thinking about the difference between your phone or your laptop talking to a data center, or for one data center talking to another data center. So the latency difference between two data centers talking to each other, or for your phone talking to a data center, is roughly the same kind of orders of magnitude as thinking of your application today here on Earth talking to something in Mars. Just in terms of the relative latencies between programs in some devices or programs that are co-located in that space, right? So if one program in one data center is talking to another program in the same data center, that's like a 1 millisecond to 4 millisecond delay, right? Like millisecond. This is like 1,000th of a second, like super fast. So if you design systems that take into account that kind of latency separation, you end up with a dramatically better system design that it ends up being much more highly scalable, that it ends up being better for applications that need to be co-located to be kind of operating in high performance and so on. And so IPC is an approach of taking that same concept and saying, if you had to design blockchains to operate really well, across planets, or conversely here on Earth, between data centers and mobile phones and browsers and so on, what would it look like? And so the structure that we arrive at is a hierarchical network where you have subnets. You make it extremely easy to generate and build and derive subnets from a root network, and every single level it is recursive, meaning you should be able to generate subnets at every part of the tree, and each subnet is a full independent chain that should be partition tolerant, meaning it should be possible to have full finality and settlement in a sub-region of that tree. So instead of thinking of one massive L1 with maybe a bunch of rollups that are super connected and where availability of the whole thing still relies on availability of the L1, imagine a setting where you have a tree of chains where at any point a subtree can disconnect from the main network and continue operating and finalizing things in its subspace. Now, of course, it couldn't transact with the rest of the network until you get, you heal that partition. But then when you do it, you can continue communicating. This kind of structure lets you do this really neat thing of saying, hey, in a subpart of the tree, we're going to do things like gate the membership by some properties like geographic locality, right? Like you can say that in a particular subnet, only certain nodes in a particular data center are going to be joining that subnet. And that lets you make the block time super short. Like you could have a 10 millisecond or 100 millisecond block time. And now you can go at proper, highly scalable data center speeds. So yeah.
That's actually great intuition. What about finality and any kind of fork choice differences, even in those partitions? So how do you actually kind of have a global consistent system that way?
Yeah, so the insight here is in using the parent-child relationship to bootstrap the security. So the things in the higher parts of the tree are more secure than the things in the lower parts of the tree, and you want to use checkpoints that give you verifiability through the parent, right? So for example, a child subnet would operate for a while using its own consensus and relying on the security guarantees there, but at a periodic interval, it would checkpoint its state into the parent to gain the security of the parent. And you can just recurse this all the way down and make it infinitely scalable. You need faster things, or you need to parallelize. You just either scale horizontally by adding more siblings, or scale
partitioning. Yep.
Yeah, exactly.
For developers who've used Git branches to their extremes, this is...
Yeah. And the cloud operates this way, right? So if you think about how the data centers work, and you have a deep network of hierarchy there. You have the data centers themselves. You have whole racks where the latencies between machines within a single rack versus from that rack to another rack is a totally different landscape. And then you have, in a specific physical server, you then have hypervisors with multiple VMs on top, and then each VM then has containers potentially, and so on. So we're taking those same kind of developer concepts and primitives to build a blockchain platform and a blockchain system, set of clients and tools and frameworks to enable developers to actually get that level of customization and scalability in their tech. And the customization part, kind of what I mean is, through Filecoin and FVM, we built this really cool structure to be able to define, both mount multiple VMs on top of the FVM. So the FVM is this hypervisor layer. You can mount multiple VMs like EVM or whatever else you want to use, and you can create a network that's specific to the application you're trying to solve. So instead of saying a general purpose public network where anybody can add any contract, imagine generating special purpose networks where you specifically pick the set of programs that are going to run in that network, and you permission it. So the nodes that you're organizing are just taking on that job. So this is precisely what a lot of groups like, say, Deepen Networks need, where they want an orchestrator to be able to coordinate thousands of nodes, and they want to very precisely run a very specific set of programs. They don't want to just run arbitrary smart contracts. They want to run a specific set of programs. And so with this, you can like take the blockchain, which is effectively this really nice kind of distributed systems orchestrator with like strong security, and then just run those programs that way, and use kind of the subnet architecture to like help these networks scale up.
I think there's some very interesting overlap with how you already touched on this actually. So the way kind of we've seen Ethereum do L2 systems, this is kind of a slight twist on how rollups effectively are being done, because now you actually have parallel rollups that are in a tree structure converging on each other.
Yeah.
But can we go a bit deeper into how does different rollups or other techniques for actually kind of batch processing transactions?
Yeah, so a key difference here is that rollups don't have their own data availability. They have to rely on some other network to give data availability. And they still rely on final settlement in the L1. And so a rollup can like accumulate a bunch of operations, but really it doesn't really happen until it clears in the L1. And that's not the case here. So in this kind of tree structure, each node in that tree is a full blockchain with finality. So you can write an application that where a sub part of the application just cares about that. So like, let's work through a super concrete example. Imagine that you're making an MMO, and in your MMO you have multiple worlds, and in each world you have multiple regions of space, and you have to deal with things like, you know, items and players fighting each other and whatnot. So things like items and, you know, an auction house or something like that, where a lot of value is being exchanged, requires a lot more security, and you probably want to put that, you know, higher in the tree. But you can partition the entire application by creating a topology where you put every world in its own subnet. You put then specific regions of that world as children subnets. And then you can run the individual logic of the game server, like the actual game server itself, with like the hits, you know, like the players, you know, casting spells at each other or whatever, directly on a chain. That's moving extremely quickly, right? Like for things like MMOs and FPSs, you need, you know, 30 to 60 operations per second. Like no chain today gives you that. And that's kind of like what you need to be able to settle with finality, right? Like if a player is like playing a game and like they're casting a spell, they expect finality. They don't want like a random rollback of like, oh, never mind, like the chain like did this other thing, or like, oh, wait 7 seconds until your spell like commits. Like absolutely, that's not how those things work. So that way you know the actual, you know, fight in a region or whatever doesn't need the same level of security that, say, like the items in an auction house or something like that require. And so you can compute all of that very quickly. You can still kind of settle it and finalize it for all the clients that care about it. And then over time, kind of externalize the results up the tree. So yeah, I don't know if that...
It actually did. So it obviously kind of... It's very easy to understand that like you can solve these deep in cases or the gaming case you talked about, or like even now social networks are possible. Are there any trade-offs that you have to make for these networks to talk to each other? Like can one game understand the assets on the other game side? And yeah, what is that complexity?
Yeah, it's a great question. So, you know, we think that the world, like already, it's kind of funny, like many years ago, like I used to kind of like talk about like how the world would have a ton of chains, and people are like, no, there's going to be like one single chain that's going to like rule everything. I was like, I don't think that's going to happen. And, you know, right now we have like a few thousand chains already. You can expect that number to go up to tens of thousands and millions eventually. And so in that world, you need extremely good calling conventions between this entire world. And today the bridge tech is like atrocious, right? Like it's extremely difficult to move state between these things. It's extremely difficult to like write programs that span multiple chains. It's extremely difficult to like interact. This is very similar to the internet before things like TCP/IP. And so we need like an extremely good set of calling conventions across this entire landscape to reason about the state moving. And that's one of the areas that like we're putting a ton of effort into, is like designing the calling conventions across this like universe of subnets, right? If you are designing for a world where you have millions of little networks, like millions of little blockchains with their own state, how do you reason about state operations and changes across all of these different logs? And how do you get like strong finality guarantees over asset exchanges that are really valuable, right? Like how do you reason about moving that state up the tree when you need more security, or how do you deal with like, some subnet, some program deeply nested calling to some other program deeply nested in some other network? Yeah.
How?
You just what I'm talking about is like you need programming language primitives that enable.
It has to be, yes, right.
So the insight is like
it has to be inherently a property of the network and not a facilitation enhancement.
No, you can do it as a facilitation enhancement, but it's much easier if you make it a property of the network. So my sense is networks are gonna enhance themselves once they see how much better it is to have that. But you can do it with any network. But the core primitive that you want here is the same thing that we've built for the traditional cloud.
Solve or create with
Yeah.
efforts.
So kind of like when I started working in the space, building, the beginnings of IPFS and Filecoin and so on, I wanted to build an institution where I could go and build open source projects and kind of scale them. At the time when I kind of looked around, I couldn't find an organization that could support building a project like IPFS to do like the long-term R&D that you need in order to build that kind of thing. And there's a lot of reasons why like large companies don't quite work for this. There's a lot of reasons why like academia certainly doesn't work. And so I built Protocol Labs to be an organization focused on the R&D pipeline itself, to try and figure out like what is it about R&D itself that is difficult, how to make it go faster, how to like do really good technology translation. So a very interesting like problem here is like when you think about like new technologies and like advancing the world and kind of like building the future, those new technologies tend to come from critical scientific discoveries. And usually people tend to think like, okay, great, like you do some science, you develop some discovery, and then magically you like have a technology and you put it into a product and you kind of like grow the product. And there's a huge gap in between those two that actually has a lot more to do with research and kind of what Bell Labs used to call fundamental development, and not kind of like the traditional product development that we do now. And that fundamental development stage is really about kind of advancing a scientific concept, like the early theory work, and do a whole bunch of research and development steps to figure out how to use that concept, that new knowledge, to then produce what eventually becomes a technology that you can then put into a product. And that part is by far the most expensive part in the entire system, and it is tragically underfunded. So for example,
expensive not just on time, but also on actual capital.
Yeah, hugely expensive in capital. So by my calculation, there's kind of like a 10 to 20x difference between the cost of doing the fundamental science work to get to the conceptual results, between that step and then the step of translating the conceptual results into a technology that you can put into a product. This is before a startup. Like this is before you have something that you can actually put
ready enough to be productized, independent of the viability of it.
Yeah, exactly. So like making it concrete, like this is the difference between, you do the conceptual research to invent the transistor. Now that you like have one big prototype, you need to like miniaturize that. You need to figure out what materials you're going to make it out of, how you're going to manufacture it, what applications does it have, and so on, until you eventually come up with like a tiny little transistor that you can then put into an actual product. And then that's the thing that you then like build into a product and sell. And so like that entire process is ridiculously expensive and underfunded because there's no kind of like public goods funding for it really. Like governments tend to fund the scientific research part, but not that part. And VC can't fund that. It's way too early. So VCs can invest in startups, but they cannot invest in that earlier space. Funny story here, like when I went around pitching PL to and IPFS and Filecoin to people, I used to kind of like have to describe like the business model of like creating a network and so on, creating this is like 2014, 2015, 2014, and they used to kind of like reference Ethereum at the time, and then usually the VC answer was, oh, Ethereum is a science project, like that's not gonna work, and
wants a world computer, that'll never work.
Yeah, and like it seemed like very hazy, and people like doing a bunch of like, again, fundamental development that wasn't yet productized, right? And so like that part like cannot be funded by VC today. It could be funded by VC fund that was like maybe one or two times larger than the biggest ones today, and maybe with a 30-year outlook instead of a 15-year outlook. But yeah.
But the interesting part here is that there's clearly that gap you've identified, and we have a kind of growing public goods funding concept in the world of Web3 here, and that ends up effectively starting a lot of these initiatives, and I know play a pretty big role in that too.
Yeah, and that's what I'm most excited about in terms of public goods funding, is the ability to use PGF structures to fund that fundamental development part that is extremely expensive and underfunded. If we can like route capital in that direction, that would be pretty great. The way that I think about it with PL is like if we can kind of generate significant returns from both investing in startups and creating new projects and new startups to then fund that stage, then we can kind of like accelerate this entire process quite a bit. And so that's the kind of like model of like what PL is. The PL is a network that enables this kind of like regen loop through the building of new technologies, new startups, and so on.
You already answered my last question. I was like, well, it looks like Protocol Labs is no longer the company that makes Filecoin. And that's because you're trying to do so much more here in terms of advancing actual technologies to get to life and be productized.
Yeah, we sort of transitioned, over the last 3 years, we transitioned from kind of a single company into a network of organizations. And now we have, probably over 600 companies in the network. And there's a whole bunch of like systems and structures that support like founders and builders to kind of like develop their projects and tech and so on. And one of the things that like I'm most kind of excited about and trying to figure out is like, how do you create like the super compelling culture of like, the most exciting kind of like high-tech startups, but in an open-ended environment that isn't kind of like blocked with like the big thick cell wall, right? Like if you think about a place like, Google in the old days, or like, you think of like Tesla or SpaceX today or whatever, they created an amazing environment inside that looks a little bit different than the rest of the world. But you have to go through this like really thick cell wall to like enter that environment. And when you enter that environment, you cannot actually collaborate with groups in another cell, right? And so what PL is trying to do is kind of like, imagine creating that kind of an environment, but without a very thick cell wall, to be able to create like a nutrient-rich environment to enable the building of these kinds of projects, but just using the tools of public capital, like building companies, building organizations, blockchain structures, communities, lean into those kinds of like public primitives in a very open, permissionless way, instead of like forcing this kind of like thick barrier of you must join as a single corporation. And we, very kind of open source and crypto native oriented way, we think like this could be like super, super powerful in creating like a very generative environment.
Amazing. Well, Juan, I want to thank you for this amazing chat, and can't wait to see IPC at even a bigger scale.
Yeah. Billions of transactions per second. You quote me on that.
Thank you so much.